In theory, theory and reality are the same. But I guess we all know what it is in reality. They're not. So let's say we conduct an experiment and we roll a perfectly fair 20-sided die 19 times. Are we going to get experimental probabilities that are equal to the theoretical probabilities? I mean, we all know that the perfectly fair 20-sided die is going to have 1/20th chance of landing on each face. Yeah, if we only throw it 19 times, we're not going to get 1/20th probability for any of the faces that actually show up. Now, if we roll a perfectly fair 6-sided die 1,000 times, or flip a perfectly fair coin 1,001 times, hey, these numbers of trials are not divisible by the number of theoretically identical probability outcomes. So no, we aren't going to end up with empirical probabilities or experimental probabilities that match up to our theoretical probabilities. Now we can conduct probability experiments with physical materials, but it gets kind of tedious if you have to actually roll a die 1,000 times. Or flip a coin 1,001 times, or whatever. So sometimes we resort to technology to run simulations, to generate large samples, a lot of trials. But there's a problem with simulations. Hey guys, assume 1/6 for each face of 1d6. Anybody who's ever played Dungeons and Dragons or any equivalent game on tabletop will recognize this notation. This is one dice, 6-sided. 1d4 would be one dice, 4-sided. So this is a tetrahedral dice. 1d3 is one dice, 3-sided, but since you can't really do that, we use a 6-sided die, and we have 1 and 2 correspond to 1, and 3 and 4 correspond to 2, and 5 and 6 correspond to 3. And then there's a 1d10 and 1d20. These are the common ones, and there's 1d100. Now for a 100-sided die, well, since that's kind of complicated to make, usually it's just two 10-sided die. You roll for the tens digit and then you roll for the ones digit. This gives you 1/100 chance, in theory, of ending up with any one of the numbers from 1 to 100. Please note that you have to come up with a way to make sure that your tens digit can accommodate a 0, whether this is subtracting 1 from your outcome or, well, having rolling 10 on the first row be a 0 at the start. Well, that depends. So, what if we want our distribution of numbers to be more towards the middle? Well, you could have, say, 11 d10 minus 10. How likely is it that all 11 of your 10-sided dice come up 1? Well, that's 1 over 10, so 1/10, whole thing, to the power of 11, which means 1 over 100 billion. So it's really unlikely to come up with the extremes if you are adding a whole bunch of numbers, but we'll discuss that sort of principle later. Now, in theory, these dice are supposed to be perfectly fair. In reality, no, sir. They are etched differently, and the manufacturing is not a perfectly homogeneous process, or they are inked differently if they are not etched. So the mass distribution varies from face to face. Therefore, the dice are not perfectly fair. Although the number of trials you would have to do to actually establish that they are unfair, unless they are very, very obviously rigged, is so large that I would not recommend it. If we do trials by simulation, though, well, we end up giving them some presets. For example, we assume that this six-sided dice, or six-sided die, because dice is plural, is perfectly fair. So if we begin with the assumption that it's perfectly fair, we are most likely going to get the experimental outcome that it's close enough to perfectly fair that we cannot tell the difference. Wait, how do we do that? Well, that's something we'll discuss a little later when we get to variance and standard deviation and all those fun things. For now, we deal with theoretical probabilities, so we neglect the reality that dice are not actually perfectly fair. And we assume that on a die, unless otherwise stated, each face has the same probability of occurring and not occurring. One face on a six-sided die has a 1/6 chance of showing up and a 5/6 chance of not showing up. This is the exact same as all the other faces. That sample space, well, that's a collection or set of all possible outcomes. Sometimes this is known as the sample set. For flipping a coin, it's heads, tails. We do not account for the idea that the coin, if you flip it onto sand, could just wedge in on its side. No, we are making things less complicated than that. So, sample space often is slightly abbreviated when we talk about theoretical probabilities compared to reality, because there are definitely people who are skilled enough to flip a coin and have it land semi-reliably on its edge. For dice, the sample space would be all the different faces of the dice. For cards, the standard 52 card playing deck has ace, and then 2 through 10, and then jacks, queens, and kings. So 13 cards of each suit. And there are diamonds, there's clubs, there's hearts, and then there's spades. Spades are generally considered the strongest, depending on the game. And then it's hearts, and then clubs, and diamonds. So these, well, there's a sample set of 52 cards you could pick. These are all the possible outcomes. However, there are many subsets for events. For example, the event of picking a 10. That's 4 of these outcomes. The event of picking a face card. Well, that's 12 of these outcomes because jacks, queens, and kings are all face cards. An event is a set of outcomes with a common characteristic. Like, say, rolling 2 dice and then getting a sum of 7. This has a number of different options. You could have the first die come up 1, and the second one come up 6. The first one could come up 2, the second one 5, 3, 4, 4, 3, 5, 2, and 6, 1. So for an event, well, the probability of the event, notice that here we're kind of making some assumptions, guys. We're dividing the number of outcomes that are in A by the total number of outcomes, so the sample set. All outcomes. Wait a second. This kind of assumes that each outcome is equally likely. Otherwise, the outcome that horse A wins versus the outcomes that horse A, B, C, D, E, all the horses in the race, any of them can win. Sir, that's not actually 1 over however many horses, because horses are different. If we have outcomes that have the same probability, though, we can organize them through a table, a tree diagram, or a Venn diagram. Now suppose we have 2 6-sided dice. And let's say we list all these possible outcomes in a table and we identify the probability of each of the sums, which are events. Okay, so we have dice 1. Well, technically it should be die 1, but yeah, usually in statistics we do not give much of a wooden nickel about the die versus dice distinction. So we could end up with 1, 2, 3, 4, 5, and 6. And here 1, 2, 3, 4, 5, and 6. Now when we're listing table cells, we list row first and then column. So this would be like this. Yeah, depending on area, you might have round brackets or even brace brackets around each of these. But here we're just listing what happens. And this means this is 1, 3. Yes, I do realize then that perhaps we should have labeled this dice 1 instead. But, well, whatever. The overall table is going to be the exact same, even if we flip it around. So 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Needless to say, most people are not very enthusiastic about drawing ordered lists of all possible outcomes for any sort of probability experiment. They tend to get pretty long. Most of us are also not fans of doing tables. This is part of why people invented permutations and combinations, so that they don't have to do as many tables, so that they can do the math easier. So here, what are the probabilities of each of the sums? Well, we can see that overall there are 36 cells here, 6 by 6, and for the sum 2, that's 1 over 36. Sum 3 is equal to 2 over 36. Sum 4 is equal to 3 over 36. And sum 5 is equal to 4 over 36. Sum 6 is equal to 5 over 36. And sum 7 is equal to 6 over 36. Hey, guys, what about 8? Well, we're going in diagonals. And after this diagonal, which is 6 cells, we get down to 5 cells again out of 36. And then for sum 9, we get down to 4 cells. Because we can have 6, 3, and then we can decrease one of them by 1 and increase the other one by 1 3 times. For P4, that's equal to P10. as we can see from the table. P11 is equal to P3, and P12 is equal to P2, in that you have to roll one particular die the first time, so 1 or 6, and then you have to roll that same particular die a second time, so you get 1 6 times 1 6 for either one of these outcomes. Of course, if you count P2 or 12, then that's 1 over 36 plus 1 over 36. But then that gets into, hey, do they overlap? Are they mutually exclusive? Which is for next section. Now let's say we have a tree diagram for 2 sequential coin flips. Identify events that include more than one outcome. A coin flip can come up heads or tails. And then the second coin flip can also come up heads or tails. So this would be heads, heads, and then heads, tails, tails, heads, and tails, tails. What is an event here that can include more than one outcome? Oh, all heads is one outcome, all tails is one outcome, but one heads and one tails? So, what's another event that can happen to have these two outcomes in this case? Well, it could be not all heads nor all tails, which would be rather different from event of half heads, half tails, if you had more coin flips.